네, 여러분 안녕하세요. 오늘 수업을 시작을 하도록 하겠습니다. 지난 시간까지 저희가 그 이상기체 상태 방정식에 대해서 배우고, 그리고 그 기체 운동 관련해서 저희가 얘기했었고, 믹스처 오브 가스스, 또 어떻게 그 다양한 기체가 믹스처된 상태에서 우리가 그 토탈 프레셔에 대한 그 각각의 기체들이 그 작용하는 파셜 프레셔를 계산할 수 있는가 등에 대해서 여러분하고 같이 이야기를 나눴었고요. 이번 시간 또 계속해서 수업을 나가보도록 하겠습니다. Okay, so hello everyone. So until the last week, so we have learned about this state of gases. So especially for the law which are the contribute to this explain about this perfect gases. We have learned about this. So based on this, so we also have discussed about this kinetic model of gases, and also we talk about this how can we derive the partial pressure of each component in the mixture of gases. So yeah, so let's continue the classes further through these classes. Okay, so this is the one example. So in our previous work, we have talked about this mixture of gases, and then actually in our real life, so usually the most of gases actually consist of the mixture. So that's why we have talked about that kind of mixture of gases actually. So this is the example. So let's see the composition of a dryer. So what this means, the air surrounding us in our daily life actually is not the single component, but that is the mixture of gases. So mostly the air consists of nitrogen. The volume percentage of nitrogen in the air is about 78%. And oxygen is about 20.95%. So actually most of the gases in air consist of nitrogen and oxygen. And there are also some few minor components such as argon and carbon dioxide and hydrogen and neon, helium, methane, krypton, nitric oxide, xenon, ozone, like this. So there are a lot of mixture of gases, and as we already told, we already discussed uh, the how can I say the pressure the exerted by this air is called as the 1 atm. Actually, this 1 atm is the made by the sum of the partial pressure of all of the exerted by all each component. So yeah, so what I want to say, the pressure exerted by this our atmosphere air is not by this single component, but this kind of a mixture of each component partial pressure. So this is the one of the things that what I want to show you. So this is just kind of common sense to help your understanding of a mixture of gases. So actually, what I want to stress out here is the most of gases actually in our real life is the mixture of gases. It's not the single component. So that's the thing. Sorry. Okay, so let's go further. And I want to solve one simple example about this state of perfect gases. So let's solve it together. So in an industrial process, so nitrogen is heated to 500 Kelvin in a vessel of a constant volume. So what this means, V is constant. And if it enters the vessel at the 100 atm and 300 Kelvin, so what pressure would be exerted at the working temperature if it behaved as a perfect gases? So what this means? So the nitrogen gases come into the vessel which have 100 atm pressure and the 300 Kelvin, and it will heat it to the 500 Kelvins with a constant volume. Then what pressure would be exerted during this working temperature? So please solve it, and I'll give you just a few minutes, and then let's solve together after that. After your the individual time to solve these things. Okay, so I hope you will just stop this movie clip and then solve this thing. Then we start to see this how to solve these things. So okay, so let's see. Let's solve together now. I hope you guys already have quite enough time to solve these things. So this is a quite simple the examples for the state of perfect gases. So basically, we will use this equation PV nRT because this is behave as a perfect gases. So okay, so let's see. So we expect the pressure to be greater on account of the increase in temperature. So the perfect gas law in the form PV over NT equal R implies that if the conditions are changed from the one set of values to another, then because PV over NT is equal to a constant, the two set of values are related to by the combined gas law. So what this means? So as you told you that the because the actually we know this PV equal nRT, then we know this R is constant. So we can rearrange this equation as NT over PV equal R. So this the condition, if the condition are changed from the one set of values to another, then you know because this value is always constant. So the true value of this involving in the change are related by this combined gas law. So what's this? So first condition, N1, T1, and P1, V1. So initial condition will be R, and the working condition is N2, T2, P2, V2 equal R. So that's why N1, T1, P1, V1 equal N2, T2, P2, V2. So so we can start this equation to calculate this problem. So because we already discussed this vessel has a constant volume. So what this means? Then V1 equal V2. And since there are no other gases applied to this system during this operating, so then the total number of molecules in this vessel will be also same. So what this means is N1 is also N2. So that's why we can simply remove N1, N2, V1, V2. Then we have T1, P1 equal T2, P2. So that's why, so what's the value we want to know is the pressure at the working temperature. So this is the P2. So therefore, we have to rearrange this into this P2 equal T1 here over T2 P1. So now we have this equation, this relationship. Then we can simply, the P1, the first pressure in the vessel is the 100 atm, and T1 was 300 Kelvin, and T2 equal 500 Kelvin. So therefore, the P2 equal 300 Kelvin over 500 Kelvin, 100 atm. Then Kelvin is removed. So in an ideal case, this P2 will be on the 167 atm. So what do you think? So yeah, so this kind of things is the problem you can solve with this kind of the state of perfect gases equation. So you can solve these things here. Okay, but actually, in the real experiment, that the results show that the pressure is actually 183 atm under this condition. So the assumption that the gas is a perfect, the ideal gases, so leads to a 10% error actually. So there is this kind of a gap between the two between the theoretical cases and experimental cases. So actually, how can I say the what I want to say is actually this case is also quite close to this the perfect cases actually. What this means there is only one single atom of nitrogen, single molecule of nitrogen, and there are no other the parts because the gases is constrained in the, the perfectly sealed vessel. So that's why there is only 10% errors. But actually, in real case, there are a lot of difference between this real value and also the experimental value. But the thing we have learned this kind of equation is because we can anyway know the trend of change of these gases. So we can think about how these kind of things will be changed in terms of condition change. So, so the expecting the kind of trend of gaseous state in some operating conditions so will help us to design some um, can say the reliable devices or reliable condition to make some kind of product so involving this gas system. Okay, so this is the things we have talked about this. So let's continue further. Okay, so until now, so we have talked about this some perfect gas situation. So, but we will now take into our attention to this real gases. So what is the difference between this perfect gas and real gases? And actually, this real gases also not these actual real cases, but we can consider a few more things to explain more about these real gases. So that things actually is the compressive process. Actually, we will talk about these things in later details. So so let's see so how this kind of real gases works in the gas state. So for the real gases, we have to consider about this molecular interaction. So the real gases show the deviations from the perfect gases law because these molecules interact with one another. So what this means? In a perfect gas situation, we only think about these electrons have a free motion. So there is only the collision during the motion of the gases inside the system. But actually, even though there are no collision, there could be interaction between two molecules. Then that kind of interaction will impact on this the state of these gases. So that's why we have to understand about the kind of interaction between these two between these individual molecules to understand about these real gases. So a point to keep in mind is that the repulsive process between some molecules assist the expansion and attractive forces assist the compression. So what this means. So in this kind of system, there is the molecules. And if there are molecules, between this molecule, this repulsive process is applied, then this repulsive force will contribute to the expansion of this system. And if there is the attractive force between these two atoms, then this attractive force will contribute to this compression of this system. So these two things you have to keep in your mind. So the key point of this real cases is the extent of deviations from the perfect behavior can be summarized by introducing the compression factors. What this means, attractive forces. So actually, I will talk about in the later more details, but repulsive forces actually is not the major factors to effect on this kind of real gases, but when these two molecules become close, then there could become the attractive forces. Then the kind of attractive forces will have the large effect on this deviation of real gases from perfect behavior. So by introducing the kind of compression factor, we can derive this the barrier or the barrier equation. And this barrier equation is the empirical extension of the perfect gas equation that summarizes the behavior of real gases over a range of conditions. So we will derive this barrier equation for these real gases in here. And the isotherms of real gases introduce the concept of vapor pressure and critical behavior. So we will also talk about the situation of the real gases in the isotherm. And the kind of the real gas in isotherm will introduce the concept of vapor pressure and the critical behavior over real gases. And a gas can be liquefied by pressure alone only if its temperature is at or below its critical temperature. So if this gases is hope to be liquefied, then we can do this by the pressure alone when the temperature is below some critical temperature. So without any, how can I say, just by controlling the temperature, we can make some, how can I say, how can I say, liquefied gases when the system is at the critical temperature or below the critical temperature. So this kind of things you have to keep in your mind, and then we will talk about these things details through these chapters. So let's see this graph to understand about the repulsive force and attractive force is applied to these two molecules in a system. So this is maybe you guys already know in your physics classes, but anyway, when there are two atoms become close, then there is some kind of force is applied to these two molecules. So there is the repulsive forces and also attractive forces. So in this kind of yellow region, so there is if there is a large separation, large gap between these two atoms, there is some kind of attractive forces. And here's attractive forces. And once this atom is close enough to this zero level, this is a zero. So if there's a minus forces, then this is the attractive forces. There's a plus, it's repulsive forces. So if this distance between the two atoms is close enough, then there could be the repulsive force applied to this system. So what this means? So repulsive force So for this repulsive forces, the repulsive forces are significant only when the molecules, the two molecules, individual molecules, are almost in contact. So what this means? So this repulsive force can be applied to system when this atom is close enough. So actually, in a situation, the repulsive force can work when these molecules are almost in contact. So they are short range interaction even on a scale measured in a molecular diameter. So what this means? So to make this kind of repulsive forces, so atoms should be really close. So most of cases the repulsive force is not dominant for this kind of a real gases, but the attractive forces are relatively the effective, even though the distance have larger than this repulsive cases. So the attractive intermolecular forces have a relatively long range and are effective over several molecular diameters. So what this means? So the repulsive forces, how can I say? It's really minor in terms of uh, the the the, uh, the the gas state, the real gas state. But these attractive forces can should be considered because the even there is the only few the molecular distance, diameter distance, but there could be some attractive intermolecular forces. Then the kind of attractive intermolecular forces can impact on this kind of the behavior of the real gases. So that's why we have to consider about this kind of attractive forces in our state of the equation for the real gases. Then that kind of consideration can the evaluate some kind of the equation which called as a barrier equation. That barrier equation is the involving this compression factors inside of it. So let's talk about the things. Okay, so as we already discussed the here, so I talked to the uh, repulsive force assist the expansion, and attractive force is assist the compression. So we talk about this in a real gas situation, the mostly the attractive forces be applied to the system. So that's why we have to mainly consider about this compression, not the expansion. So by including these compression factors in this real gas state, then we can get some kind of equation to explain about this real gases. So that's why we have to talk about this compression factors. So this compression factor called as G or jet of a gas, and is the ratio of its measured molar volume. So yeah, so the measured molar ratio is a Vm. So what I mean, this is the real gases volume molar volume, which is the total volume over the number of atoms, and the molar volume over perfect gases will be expressed as the V0n at the same pressure and temperature. Then this compression factor jet is expressed as the molar volume of perfect gases over the molar volume of real gases. So as we talk, this PV equal nRT. This is for perfect gases. Perfect situation. And this V can be written as the, how can I say, V0M equal N over V for perfect gases. So we can just say V0. Then this V will be N V0N. Then we can remove this one. So that's why V0M equal P over RT here. Okay, so then as we told you, Z equal V0M over Vn, and V0M equal PRT. So that's why Z equal RT over PVM. So we can simply make this system as PVM equal RT Z. So this is the equation considering this compression factors. So because the for perfect gases Z will be 1, you know, because the in perfect gases the Vm will equal Vm0. So that's why the Z will be 1 for this perfect gases under all conditions. So the deviation of Z from 1 is a measure of departure from perfect gases. So if we measure some kind of a volume of real gases, and we can simply dividing it by this V0N, I mean for the perfect gases volume, then we can have a deviation of Z from 1. Then that is the departure from the perfect gases. So this is kind of an experimental situation. So during this situation, the for all conditions, the Z will be 1 for ideal case, but depending on the gases, there is some deviation. So this is hydrogen and methane and ammonia. So this kind of different gases have this deviation. So the kind of deviation is the how can I say, so influenced by some kind of condition of each component of these gases. So we can simply consider about this jet for explain about the deviation of the gases from this real the perfect gases. Okay, so with this kind of a compression factor, we will go further about this Brière coefficient, which will be discussed here. Okay, so Brière coefficient is explain about this how much the how can I say how much the kind of departure of the real gases by this compression factor is occur from this by using this kind of compression factors. So what this means? So this is kind of the how can I say, the one of the, how can I say, it's a method to explain about that kind of deviation. So for example, so actually we have talked about this this one. So we can have PVM equal RTZ, which is the including this compression factor for these real cases. And this viral coefficient is the viral equation of stasis can be start with this PVM, so RT, and this deviation of Z will be expressed as the this kind of the factors. So we can simply this is kind of a deviation coefficient, deviation factors. So if the how can I say, the ideal cases, then this deviation factor will be 0, and only one will be called as Z. So you don't need to worry about how can we derive this kind of things, but this is just kind of mathematical how can I say, the expressions, the mathematical way to express this system, the coefficient. So you can just think about this. This is a way to explain about this coefficient for this kind of Z value of real gases. So we have this kind of things. Then this can be written as the function of the volume Vm. So the final form of this spiral equation is the here. So what I want to say, so you don't need to think about this. So why this kind of equation comes, but this is kind of mathematical way, and so this is the more generally used form of this the Birrier equation. So you can use this one. So the depending on the deviation of real gases, then we will have this kind of coefficient to see the how can I say, the explain about this real gas state. So for example, so if there is this kind of the Z value, and there is some kind of a deviation here, then the way to express about this kind of graph is by using this kind of equation. So depending on the coefficient, depending on the graph, we can get this coefficient vectors. So depending on the shape of this graph, these vectors can be also determined. So that's why this B is a second Birrier coefficient and C is a third Birrier coefficient. And if there is no more, if there are more the variation from these things, then we can add some more D, E, F like this. This is just kind of mathematical way to express about this equation, the behavior of the real gases graph. So this is the start of the Birrier equation coefficient. So actually, what can I say, because this Birrier equation is the the how can I say the function of pressure and the deviation of jet value. So the how can I say the let's see. So PV equal I can say RT1 V1 So that's why the we can simply think about this the anyway when we make this kind of the graph, the slope of this graph can be dp over dz, and this will be this kind of equation. So this is kind of coefficient. So we have to here we just need to know about this physical meaning of this thing. So when the pressure becomes the zero, then there is the only coefficient of the b prime. I mean the second Billiard coefficient. So actually, this is kind of how can I say? It's the example. So if you don't need to relate this, correlate this previous system. So if we have this kind of a pressure versus the compression factor jet graph, then actually for the perfect gases, the dp over dg will be zero, right? Because there is only jet, there is no change of jet, because for perfect gases, jet is always 1. But in the real case, there is some kind of a slope, then we can have a dp over dz as like this. Then if pressure becomes 0, then finally we have only this the deviation factors, so b prime. So that's why it's, even in real cases there is the this kind of deviation, which is comes from the compression factors of real gases. Then we can also express this one as the volume factors. Then if volume becomes large enough, it's infinite things, then this will be reach to this B. So here actually the thing is that we have to how can I say the understand about this kind of the state of real gases. So what this means? So by including this kind of compression factors, so there's always some kind of deviation of state of real gases from this perfect gases. Then that kind of deviation can be present by this kind of things, mathematical situation. So what this means? So actually, this is the how can I say oppositely derived from this the experimental result actually. So this is not that kind of theory. So you don't need to memorize these things actually. So you just think about this. There's a deviation. So when we how can I say so draw this kind of pressure versus compression graph, and for perfect gases has this kind of slope. And in real cases, there is this kind of different behavior. Then we need to have a way to express about this kind of result. then we can simply use some mathematical way to explain about these things. And this is also same situation. Then even though pressure becomes zero, then this the graph slope is the approach to some point, and we call that kind of things as a Billiard coefficient. And also, if we draw this graph as a function of volume, then also we can make this kind of the values for this Billiard coefficient. So this is only some kind of way. So yeah. So actually, the thing is actually you have to remember here actually it's a boil temperature. You might be heard many times about this boil temperature. So this boil temperature comes from this graph. So this is the perfect gases, and this is the high temperature case. This is a lower temperature case, and in some temperature case, there's some this graph comes from this zero pressure, but in some point this G value approaches to 1, and just keeping the value 1 and approach to this zero slope. So that kind of situation, temperature, make this kind of a graph called as the boil temperature. So this is some example, the second viral coefficient, which is determined by some kind of experimental result. So from this experimental result, we can have this kind of viral coefficient. So actually, the second viral coefficient is the one of the most important factors for explaining about this the real gas state, because the shape of this graph is mostly determined by this second viral coefficient, and the other third or fourth coefficient can impact on this some minorly. So that's why we have to first know about this second viral coefficient. Okay, so this is the other thing, the condensation. So now we know this some real cases, real gases volume. We also measure pressure. And in the certain temperature, as the volume is decreased, then pressure will be increased. And in a certain point, there is this kind of pressure drops, and this is because of this phase transition. So what we will learn in later phase transition. So the how can I say, in this point the vapor, I mean gases, so become liquid, and then when that gases become liquid, then pressure will be decreased dramatically. So the kind of process called as the condensation. And there is one also important terminology, which is the vapor pressure. So in this vapor pressure, the pressure corresponding to the line of this CDE. So what this means? So let's see. So when both liquid and vapor are present in equilibrium, it's called as a vapor pressure of the liquid at the temperature of this experiment. So how can I say? So at the temperature of 20 degrees C, this gas will be compressed as the volume shrinks. At a certain point, the how can I say, the vapor is started to transit as a liquid. Then in this case, there is the system consists of a vapor pressure plus liquid, and this two phase is in equilibrium. So that's why there is no pressure or change in this line. And if the how can I say, the pressure is the kind of equilibrium states occur, called as a vapor pressure. So this is one of the famous terminology, and this is the why this real gases. Okay, so there is also a critical constant. So what is a critical constant? So we normally say some kind of critical points as, for example, if there's a critical temperature, then we call it TC or VC. So critical volume is VC or critical pressure PC. So this kind of critical point means the point where some kind of transition is occurred. So for example, if some kind of vapor transit into the liquid, and the temperature point at that transition are called as the critical temperature. Then if there is some kind of the transition of the vapor into some kind of liquid, and the point of volume at that time are called as a critical volume. So actually, the kind of critical constant is the concept is quite normally used to design some kind of the condition for the process of some product. And here we would like to also know this supercritical fluid. And what is a supercritical fluid? Is the concept is the single phase that fills the entire volume when this the temperature of the system is larger than Tc. And this single phase may be much denser that we normally consider typical of gases. So what this means? So how can I say? The point of this supercritical fluid is that there is only single phases in the system, which is when the temperature is above at this Tc, critical temperature. So at this critical temperature, above this critical temperature, we cannot see any other phases in the system. So what this means, if we have some kind of, okay, so for example, the oxygen of Tc is 155 Kelvin, and over this 155 Kelvin, there's only gas phases of oxygen in the system. We cannot find the liquid type of oxygen in this system. So the kind of the oxygen above this Tc may be much denser than we normally consider typical gases. So for example, this carbon dioxide, so the critical temperature of carbon dioxide is about 300 Kelvin, 304 Kelvin. So above this 304 Kelvin, usually the carbon dioxide, there is only the, how can I say, the gas phase of carbon dioxide, and you cannot see any other types of carbon dioxide. So this is the supercritical fluid. So yeah, so you might this is kind of a common sense that you might see this kind of terminology in your professional life. So at the moment you will remind this kind of a concept. Okay. Okay, so let's solve a simple example also about this real gases and also Fourier equation. So the example is there is the oxygen gases, and that oxygen gas has a volume of 0.225 with a 0.104 mole at this temperature is 100 Kelvin. And so what is the pressure? So please find the pressure using this Fourier equation as below. So I'll give you a few minutes to solve this equation. So solve these examples. Okay, so let's solve together. So first of all, to solve this system, we have to find this Vm. So Vm is the n to over V, and this is the NO2 is the 0.104 mole, and volume is the 0.225 decimeter 3. And if you do this calculation, then we have 2.16 decimeter per mole. And for more simplification, you can press this as 2.6 10 minus 3 eta 3 more. Okay, so now we have this equation. And since the P equal Vm RT, and here we can just find this second Vieira coefficient. So that's why we only have this one. P Vm over RT and 1 plus Vm over B. And so we have to know this B. And this B value we can find here. No. Uh, yes, so unfortunately there is no B value for this option, but yes, I'll give here. So you need to worry about the things. If this kind of problem set is presented in the midterm or final term, then I will give all these kind of vectors. Okay, so anyway, the uh, B value of oxygen is the 1.975, 10 minus 4 meter more, this one. So let's just solve it. So this one here, and VM is the 2.16, 10 minus 3. Yeah. And R is the 8.31 5 joule more per Kelvin, and the temperature is the 100 Kelvin. This is minus. And 1 minus Vm over this B minus 1975 here. So you can simply limit this one, and here this one, this one, this one, this one. So finally, we can have, you can just simply calculate this one. Then we will have 3.50, 5 joule meter. Then because the 1 Pascal equal 1 joule meter minus V. So that's why we can say that this is as 3.5, 10, 5 Pascal. And or we can simply say that the 350 kilopascal. So yeah, so actually, yeah, so this is the value. So if you solve this thing with the state of perfect gas equation, then you will get this 385 kilopascal. You can see there is almost 10 points deviation. So this is because the B value is quite large. So Vm over B is around 0.1. So this is quite larger than quite have a quite big difference from this ideal gas object, which is the one. So that's why there's some big difference here. So this kind of things you are can I say that you can calculate this kind of a problem from this kind of the how can I say the knowledge. Okay, so I think we'd better stop this class here. And before the stopping, I'll give you a quick summary in Korean for the content we have learned today. So if you understand all things, you don't need to listen about my Korean voice, actually. So I also upload some homework in the e-class. So please find the things here. 네, 수업을 이제 좀 마치도록 하겠습니다. 그러니까 간단하게만 제가 정리를 좀 해드리고 수업을 좀 마무리해 보도록 할게요. 그래서 일단은 뭐 여기부터 시작을 했죠. 요거는 이제 지난 시간에 조금 더 말씀을 드렸어야 되는 건데 말씀을 마저 못 드렸던 건데 실제 우리 삶에서의 모든 가스들이 믹스처다. 그래서 우리가 지금 생각하는 것처럼 어떤 싱글 기체에 대한 어떤 방정식으로 우리 어떤 일상생활을 표현하기는 어렵다. 하지만 여러분이 이제 나중에 이제 실제로 이제 프로페셔널 어떤 필드에 가셔가지고 접하게 될 그런 화학 공정들이라든가 이런 것들에 대해서는 그런 싱글 페이지도 많이 접하긴 하죠. 그래서 뭐 그런 것들의 예시를 이제 공기로 보여드린 거고요. 그리고 요거 같이 한번 풀어봤고요. 뭐 간단하게 왜 리얼 가스와 퍼펙트 가스일 때 이게 어떻게 아톰이 존재하는가 하는 거 봤었고, 그리고 사실은 이제 우리가 더 관심 있는 건 이제 리얼 가스, 그러니까 실제 가스 상태에서의 어떤 기체의 상태를 우리가 아는 것이 되게 중요한데, 그거에 대해서 여러분하고 얘기를 드렸었죠. 그래서 이 실제 가스에서 우리가 퍼펙트 가스와 좀 다른 점이 발생한 이유가 이게 가스들끼리의 어떤 인터랙션이 존재하기 때문인 거죠. 그러니까 가스들끼리 있을 때 서로 어트랙티브한 펄스가 발생을 한다던가 아니면 서로 리펄시브한 펄스가 발생하게 되는데 그러한 어떤 어트랙티브한 리펄시브한 펄스가 발생하는 거에 의해서 실제 퍼펙트 가스에 대한 상태 방정식이 적용이 안 되는 상태 방정식과 다른 값을 나타내게 되는 경우가 생기는 거죠. 그래서 이제 그런 것들을 이제 쭉 설명을 드렸고요. 그런 것들을 설명하는 것 중에 가장 핵심적인 것 중에 하나가 바로 이 컴프레션 팩터가 있었죠. 그래서 뭐 뒤에도 설명을 드리겠지만 이 어트랙티브한 펄스가 미치는 영향이 리펄시브한 펄스에 미치는 영향보다 더 크기 때문에, 그러니까 더 쉽게 나타날 수 있기 때문에 이런 컴프레션 팩터에 대해서 얘기를 한 거고요. 네, 그래서 그런 내용들을 여러분하고 이야기를 좀 드렸었죠. 그래서 지금 리펄시브 폴스랑 어트랙티브 폴스에 대해서는 얘기를 드렸었는데 어, 아톰의 간격이 좀 먼 경우에, 그러니까 몰레큘 간의 어떠한 디스턴스가 좀 있는 경우에는 보통 이제 어트랙티브 폴스가 보통 걸리죠. 서로 이제 잡아당기는 힘이 걸리는데 이게 이제 리펄시브 폴스가 걸려면 이제 서로 간의 어떤 핵들끼리 밀어내는 이제 힘이 발생을 해야 되는데, 그러기 위해서는 이게 아톰들끼리 거의 붙어 있는 경우, 굉장히 디스턴스가 거의 보이지 않는 그러한 상태인 경우에 대해서 이런 리퍼시브 포스가 발생을 한다. 음. 그래서 이런 실제적으로 이런 리퍼시브 포스를 우리가 고려해야 될 케이스는 굉장히 조금 마이너하다. 뭐에 비해서 이런 어트랙티브 포스에 의한 어떤 그 팩터가 발생할 때에 비해서. 근데 이제 아까 말씀드렸다시피 리퍼시브 포스는 이제 그 뭐냐 텐션, 그러니까 그 익스펜션, 어떤 그 팽창에 기여를 하는 거고, 어트랙 포스는 이제 자기들끼리 잡아당기니까 컴프레션에 이제 기여를 하게 되는 거죠. 그래서 우리가 이제 실제 가스에서는 그런 인터랙션 중에서 어트랙티브 인터모레큘러 포스가 그 인터랙션을 미치는 영향이 크기 때문에 실제적으로 우리가 컴프레션이 그 기체 스테이트에 그 미치는 영향을 우리가 고려를 해야 됩니다. 그걸 나타내 주는 게 바로 이 컴프레션 팩터라는 거고, 여기서 제가 이제 사실 뭐 이런 수식들을 많이 이제 설명을 드렸는데, 이게 일종의 하나의 어떠한 그 도출된 시로 보시면 돼요. 그러니까 어떤 뭐 원리에 따라서 이렇게 만들어진 거라기보다는 실험적인 어떤 내용들을 바탕으로 해서 이게 이런 식으로 따라간다고 도출된 거라고 보시면 되고, 뭐 그 중에서 이제 중요한 게 바로 이런 G 팩터가 있었죠. 이게 어, 이상기체일 때랑 실제 기체 사이에 볼륨의 차이를 나타내는 게 G 팩터였고, 이거를 컴프레션 팩터 G라고 했고, 그러니까 이 G 값이 G 값이 작아지면 실제 기체 퍼펙트 깼을 때보다도 컴프레션 많이 된 거기 때문에 그런 이너모레큘러 어트랙션 포스가 많이 작용을 하는 케이스가 되는 거죠. 그래서 우리가 그거를 고려해서 나타내는 리얼 가스에 대한 방정식이 바로 PVM, RT, Z 되는 거고, 퍼펙트 깼을 때는 Z가 1인데, 이제 이 Z가 1인 거에서 벗어날수록 실제 그 리얼 가스에 미쳐지는 컴프레션 팩터 영향, 그러니까 어트랙티브 포스 영향이 커지는 거죠. 그래서 요거 보시면 지금 요게 지금 G값이잖아요. G값이 1일 경우가 퍼펙트 가스인데 실제 가스들이 G값이 1이 아니죠. 그러면은 압력에 따라서 이렇게 G값이 이렇게 지금 변하고 있어요. 그래서 지금 보면 이런 거를 저희가 했었어요. 그, 어, 이 식을 이제, 이게 사실 많이 쓰이는, 그 중에 이제 그 비리얼 이퀘이션이라는 게 있는데, 비리얼 코에피션트라는 게 뭐냐면, 어, 이런 집값에 의한 그 차이를 나타내기 위해서 이런 실제적으로 수학적으로 이렇게 나타냅니다. 이게 결국 몇 급수거든요. 몇 급수. 그러니까 이러한 그 실제적으로 그래프를 그리면 이렇게 그래프가 나오게 되는데, 이런 그래프를 지금 수학적으로 나타낸 거예요. 그러니까 이게 뭐 어떠한 어떤 공식에서 만들어진 게 아니라 그래프를 우리가 그 그래프가 어떻게 실제 가스에서 그래프가 어떻게 나타나는가 하는 거를 대충 이런 식으로 그래프를 만들 수 있다 하는 걸 이제 보여주는 거고, 그래서 이러한 이게 다 코에피션트들이죠. 이 코에피션트들의 값을 우리가 뭐 결정을 하면은 요 어떤 그 실제 리얼 가스 상태에서의 그 가스 상태를 우리가 좀 알 수가 있다. 네, 그래서 이 코에피션트가 중요하다. 이제 좀 생각을 하시면 되는데, 그래서 지금 보면 뭐 이거를 그래서 실제 이제 가스 상태를 이렇게 보면 이런 식으로 기울기가 이렇게 나타나게 되잖아요. 그래서 이런 기울기들을 우리가 계산을 해주면은 이런 B 값이나 이런 세컨드 바이럴 그 코에피션트 같은 걸 우리가 계산해 줄 수가 있다. 쉽게 뭐 그렇게 생각을 하시면 될 것 같고, 그 중에 이제 뭐 보일 템퍼러처라는 게 있는데, 보일 템퍼러처는 이 그래프가 이렇게 보시는 것처럼 0에 수렴해질 때 이 끝구간에서 이렇게 1에 가까운 상태에서 1에 가까운 상태에서 이렇게 수렴을 하는 경우, 이런 경우를 우리가 보일 템퍼러처라고 합니다. 지금 그런 거를 나타내는 어떠한 경향이 보이는 경우를 보일 템퍼러처라고 하고 있어요. 그래서 어쨌든 간에 이런 식으로 구해주면 이런 식으로 B값을 계산해 줄 수가 있고, 나중에 뭐 시험 볼 때 이 B값을 구해라 뭐 이런 거 없습니다. 이런 건 없고 그냥 전체적으로 이 흐름이 이렇게 된다는 것만 여러분 이해를 하시면 돼요. 그래서 요 B값 같은 경우에는 뭐 계산하는 문제가 있으면 요거를 우리가 주어진다. 그래서 그렇게 푸시면 될 것 같고요. 그럼 뭐 컨덴세이션이라는 게 있는데 당연히 이제 볼륨이 줄어들면서 이런 식으로 응축이 일어나게 되는 거죠. 근데 그 중에서 우리가 뭐 알아둬야 할 점이 베이퍼 프레셔라는 게 있고요. 베이퍼 프레셔는 기체와 공기가 평형으로 혼재하는 상태. 그래서 더 이상의 어떠한 그 프레셔 변화가 일어나지 않고 볼륨 변화만 나타나는 일종의 상변화가 나타나기 때문에 이런 게 발생하는 거죠. 그래서 그거를 우리가 베이퍼 프레셔라고 한다. 이런 거는 여러분이 약간 상식적으로 알고 계시면 좋죠. 그리고 이 슈퍼 크리티컬 플루이드, 이제 크리티컬 포인트라는 건 여러분이 알고 있죠. 어떠한 그 물질의 특성이 이렇게 딱 변하는 그런 임계점들 우리가 크리티컬 포인트라고 하는데 그 중에서 특히 슈퍼 크리티컬 플루이드라는 것들이 있습니다. 이게 뭐냐면 뭐 초임계 유양, 뭐 초임계 유동체 뭐 이런 식으로 한글말로 얘기를 하면 될 것 같은데 그러니까 이 슈퍼 크리티컬 플루이드가 발생하는 그 온도, 그러니까 TC라고 하는 임계 온도 이상에서는 그 기체가 그 시스템에서 싱글 페이지로 무조건 다 존재를 한다. 그리고 그 싱글 페이지로 존재할 때 우리가 생각하고 있는 원래 이상 기체에 비해서는 조금 더 응축된 형태로 존재할 수 있다. 뭐 그렇게 좀 생각을 하시면 될 것 같고 이 슈퍼크리티컬 플루이드 그러니까 우리가 알고 있는 대부분의 기체가 지금 슈퍼크리티컬 플루이드를 지금 있는 거죠. 그럼 산소 같은 경우에는 155 켈빈이 크리티컬 템퍼러처인데 지금 우리 온도가 한 297 켈빈 정도 되니까 상온이 그러면 뭐 그 산소는 항상 고체로 있을 거고 CO2 같은 경우에는 뭐 다른 상이 존재할 수 있는 거죠. 왜냐하면 304 켈빈이니까 실질적으로 상온에서 다른 상이 존재할 수도 있는 거죠. 그래서 이런 문제도 한번 풀어봤고요. 그래서 뭐 그렇게 어려운 내용들은 아닙니다. 지금 여러분이 어떠한 그 리얼 가스와 이게 지금 막 수식들이 많이 나와서 조금 헷갈릴 수가 있는데 뭐 이런 것들을 여러분이 막 유도하고 막 이런 거를 하는 지금 그런 시간은 아니고 그냥 이런 게 있어서 어떤 팩터들이 있다. 그래서 이런 BDR 팩터라는 게 있어서 이게 컴프레셔널 관련한 팩터고 그래서 실제 값과 아이디어 퍼펙트 가스와 리얼 가스 간의 어떤 이런 차이들이 발생하고 그러한 차이들을 뭐 이런 식으로 간단하게 계산을 한번 해볼 수 있다 뭐 하는 것들에 대해서 여러분이 좀 해볼 수 있는 거죠. 네. So okay, so now I also finished this Korean summary too. So let's stop this class today here and see you on next classes. So please keep in mind that I will give you homework. Then you have to keep the due date, and because I cannot accept this any homework after due date. So okay, so thank you for your attention and see you next week.